Hello again. The last section of chapter 9 that we cover in this class, models for population growth. These are basically two differential equations, one called the law of natural growth and the other one called the logistic growth model. So the first one we will develop quickly. You've seen this before, this is not new. So we have the rate of change of the population, rate of change of population with respect to time, P with respect to time is directly proportional K times P. Inversely proportional would be K over P, inversely. But it is directly proportional with P, with the population size. How do we solve this differential equation? We separate the variables as we did before. dP over P equals K dt. Now we are ready to integrate both sides, so we get natural log P in absolute value, of course, equals KT plus a constant C. Nothing new here. We need to change this into an exponential. E to all this equals the absolute value of P. So we did this again before. So this is E to C, which will be replaced by P0 or P at 0, initial population. And of course, P equals plus or minus the initial population times E to KT. But of course, the initial population cannot be negative. So the general solution of this differential equation, this one, of course, is going to be P of t equals P0 e to kt. We've seen this from algebra. And I like to look at one example. But these examples, these problems are in section 3.8. So here's the best time to present one. I'm on page 2. So let's look at problem 3 on page 245. A culture of bacterium initially contains 50 cells. So then I know that P0, which is P at 0, 50 cells. When introduced into a nutrient broth, the culture grows at a rate proportional to its size, okay, which means P of t, as we know, P0 e to kt. After 1.5 hours, the population has increased to 975. So we are given a point. Point is t comma p, t 1.5 hours, and the population increased to 975. So t in hours. Good. So the first question here is find an expression for the number of bacteria after t hours. So we do have P0, which is, or P sub 0, which is, or P naught, which is 50. But I don't have the growth rate. But that's okay. I have this point. When P is 975, T is 1.5. So 975 equals 50 because that's what P0 is. E to 1.5K. Again, from algebra, we'll divide both sides by 50 and then apply natural log. So 975 over 50 equals e to 1.5k. I apply natural log, 975 over 50. I apply to this side, so I have to divide by 1.5. So that's what would be our k. So when we plug it in the graphing calculator, if I manage to find my calculator, yes, it's here. And when we plug in natural log, in parentheses 975 divided by 50, close the parenthesis, and then further divide by 1.5. And we get always k with at least 4 decimal digits, 1.9803. We will put it back in the model. So P of t equals 50 e to 1.9803 t. So we answered part A, in which we determined the expression for the number of bacteria after t hours. Find the number of bacteria after 3 hours. That's a piece of cake, right? We have to find P of 3. So no problem, 50 E in parentheses. I'm going to recall the previous answer, so 3 times the previous answer to have as exact as possible. Okay, and that is 19,113 cells. Okay, part C, find the rate of growth after 3 hours. Well, remember what we have to do. We have to find P prime of 3. This is the growth rate after 3 hours. And the measurement unit here, whatever we get, first of all, we have to find P prime of t. But whatever we get, the measurement unit has to be in cells, Y measurement unit, per hour. Cells per hour. Oops, not per year. Cells per hour. So before we do that, we have to find P prime of t and then plug it in. And I just want to make sure that no one gets confused over there. Okay, so let's differentiate. So we already know that dp over dt equals k times p. However, since we have the formula, we can also find P prime of t if you want as 50 times 1.9803 times e to 1.9803 t. So when we multiply 50 by 1.9803, we get 99 P prime of t, 99.1015 e to 1.9803 t, and now we want P prime of 3. So this number multiplied by e raised to, and the power is 1.9803 multiplied by 3. And I got 37653.13, and this is cells per hour. So see, I'm going to copy it here so I don't leave it blank. 653.13. Let's see, there is also after how many hours will the population reach 250,000? So that's the last question here. So in part D, 250,000 equals 50 times e to 1.9803 t. Again, this has nothing to do with calculus, it's just algebra. I will simplify, I will divide by 5 and I get 5,000. I will apply the natural log and I get here 1.9803 t, and t will be natural log of this over natural log of 5,000. If you want, with parentheses or without, it's just one number, it's okay, 1.9803. And when we calculate this, natural log 5,000 divided by 1.9803, and we get 4.3 hours. So T, 4.3 hours. Now, finally, let's look at the other one, the other differential equation, which is the logistic growth model. And on this one, I'm just going to give you the final results. So the logistic growth model. Okay. dp over dt, the same thing. The population, the rate of change of population with respect to time is this time k, is still a constant. The initial, the rate of growth of population with respect to time is the population multiplied by a constant k. However, it also follows with another factor, which is 1 minus p divided by m. P is the same population, but what is m? Well, m is the maximum capacity that the environment sustains. It's also called the maximum capacity or the maximum population that the environment can sustain. Okay, so let's take a look and see how we solve this. I forgot this is page 3, and this is my page 4. Okay, so when we go through the steps of solving that differential equation, the final answer, the population function, will be 1 plus a over e times e to negative kt, where a is a constant. It's determined by subtracting from the maximum capacity the initial population and divide by the initial population. So again, we already know that. Let me write it again. P0 is P of 0, so initial population. So let's look here at a couple of examples and see how this works and how we determine solutions for differential equations that are logistic models. Okay, so let's look at 5 on 639. And we have the Pacific halibut fishery can be modeled by dp over dt equals k p 1 minus p divided by m. Okay, where p is the biomass in kilograms of the members of the population at the time t, and t is measured in years in this problem. The carrying capacity, that's what I meant, maximum capacity, or also called carrying. Carrying capacity or maximum capacity is given to us in the problem as uppercase M, of course, 8 times 10 to the 7th kilograms. And we are also given the constant, which is 0.71 per year. In part A, they're telling us that P of 0, or P0, same thing, is 2 times 10 to the 7th kilograms. Find the biomass a year later. So we are really asked to find P of 1. Good. So we have the solution to such a logistic growth model. We have to determine A, this constant here. We have K, we have M, so we can create the model immediately. So first of all, A is M minus P0 over P0. And M is 8 times 10 to the 7th. P0 is given to us as the initial population as 2 times, right here, 2 times 10 to the 7th, divided by 2 times 10 to the 7th. So 8 minus 2 is 6. 6 divided by 2 is 3, because 10 to the 7th factors out. So then we are ready to write the model, which is 8 times 10 to the 7th over 1 plus 3 e to negative 0.71 t. So we have the formula. We are asked to find a biomass a year later, no problem. So here we only have to determine P of 1. So with the graphing calculator, I will type in 8 divided by, in parentheses, 1 plus 3 and e to negative 0.71 times 1. Close the parenthesis for the power, close the parenthesis, and then don't forget to multiply this by 10 to the 7th. So 3.23 times 10 to the 7th, of course, kilograms. There is also part B here. How long will it take for the biomass to reach 4 times 10 to the 7th? Again, this has nothing to do with calculus. This is all algebra. Okay, so we have in part B, 4 times 10 to the 7th equals this. 8 times 10 to the 7th over 1 plus 3 e to negative 0.71 t. When will the biomass be this? So I'll simplify both sides, dividing both sides by 10 to the 7th. I'll divide both sides by 4. I'll cross multiply. 1 plus 3 e to negative 0.71 t equals 2. Subtract 1 from both sides. So I have 3 e to negative 0.71 t equals 1. Divide both sides by 3 and apply natural log. So negative 0.71 t equals natural log of 1/3, or t equals natural log of 1/3 divided by negative 0.71. So t, when we divide all this, I got natural log 3 divided by 0.71, or the way it is right here, it's okay, 1.55 years. Okay, so let's look at one more question. Question 7, problem 7, same page, 639. Suppose the population grows according to a logistic model, fine, with the initial population, they say 1,000, carrying capacity or maximum capacity 10,000. If the population grows to 2,500 after 1 year, we're given the point. So t in years. So after 1 year, the population is 2,500. What will the population be after another 3 years? So in other words, they're asking us to find P of 4. Okay, all we have to do is just solve the equation, the differential equation. Find A first, m minus P0 over P0. So m is 10,000 minus 1,000 divided by 1,000. 9,000 divided by 1,000 is 9. Next, we write the solution, which is P of t, is the carrying capacity or maximum, in other words, 10,000, divided by 1 plus 9 e to negative kt. At this point, we have to determine k, plugging in this point. Which point? When t is 1, P of 1 is 2,500. So 2,500 equals 10,000 over 1 plus 9 e to negative k, because t is 1. Cross multiply. What I like to do is just simplify already. 25 by 25, and I have here 4, and I have here 1. Cross multiply. 1 plus 9 e to negative k equals 4, or 9 e to negative k, subtract 1 equals 3, or e to negative k equals 1/3, or negative k equals natural log of 1/3, or k equals natural log of 3, because we multiply both sides by -1, and 1/3 has power -1. So always for k, 4 decimal digits. So natural log 3, I got 1.0986. So minimum 4 decimal digits. Okay, so all I have to do is just plug it back in. So P of t equals 10,000 divided by 1 plus 9 e to 1.0986 t. And now they're asking us to find P of 4. We plug in with t equals 4, and I got 9,000. I hope this is helpful and you understood what we did. Thank you.